Hi, my name is Emmanuel Etikodo and I'm currently taking Physics 22 to our Jira Tech, and this is my lab report on magnetic braking with Faraday. Key ideas relevant to this lab involve the magnetic field of a bar magnet on axis, which is also the same magnetic field of a dipole, magnetic flux and EMF, Faraday's law, Ohm's law, Lenz's law, and momentum principle, something we used back in Physics 2211. The purpose of this lab is to explore magnetic braking through the interaction between a falling magnet and a tube of aluminum foil, both in the lab and computational. Here you could take a look at some of the formulas that we use in the lab, which are basically formulas for the key ideas we discussed on the previous slide. This is my experimental setup. As you can see, I dropped a bar magnet through a tube of aluminum foil. I've labeled the dimensions on my diagram and have provided measured values gotten from the lab to the right. The magnetic moment of the power magnet, which is found to be 3.21, and also after 5 trials I found the average time taken for the magnet to fall through the tube to be 1.298 seconds. Looking at my computational model, in step 1 I defined the geometry of the tube, and in step 2 I defined the magnetic field of a dipole at any location. In step 3 I calculate the time derivative of flux, and in step 4 I find the current through a single ring of the tube. In steps 5 and 6, I calculate the force by the induced current on the falling magnet, and in step 7, I calculate the force due to gravity as well as a net force, which takes into account the force due to gravity and the force due to the induced current. Finally, in step 8, I apply the momentum principle to iteratively update the position and velocity of the magnet as it falls through the tube. Looking at the output of the program, we could see the magnitude of velocity initially increasing before it decreases and settles at roughly 0.24 meters per second for approximately a second before the magnet reaches the end of the tube and falls through completely. The predicted time taken is 1.322 seconds, and as we mentioned earlier, the actual time was 1.298 seconds, average over 5 trials. Now for the discussion questions. For the first one, applying Lenz's law, it becomes apparent that red corresponds to counterclockwise and blue to clockwise, as this is the combination that will slow the magnet down. If we flip the magnet, well, nothing will happen. It will still be slowed down as before, only this time the currents will flow in opposite directions to what we see right now. How the time calculation in the model compares to real world results while accounting for possible sources of error. We could have made our model better by splitting the tube into more rings so as to obtain a more accurate result, and also account for any resistance the magnet might encounter on its way down the tube. As for the shape of velocity versus time plots, what does this tell us about the forces on our back magnets? Well, we can see that the forces are unbalanced in the first section of the graph when the speed is increasing. The forces are further unbalanced in the other direction when the speed is decreasing, and the forces briefly balance for about a second during the flat section of the graph. Finally, the forces are unbalanced again and the speed increases additionally. Now for the what if question. In the first one, if the resistivity approaches zero, the force pushing the magnet up increases until a point is reached when the force on the magnet is large enough to stop the magnet from falling through the tube at all. And lastly, what will happen if it cut holes in the tube? Well, it's hard to say without actually doing the experiment. But what will likely happen is that this will disrupt the normal flow of current in the tube, therefore thereby reducing the extent to which the aluminum tube is able to apply a braking force to the falling magnet. This will be due to a reduced amount of current being able to flow through the rings of the tube. Thanks for watching.